Okay, the next speaker is Professor Ageev. Title of the talk: effective quantum field theories and ultrametricity.
Okay, thank you very much for possibility to give a talk here. It's a great pleasure for such a newbie in p-Adic mathematics like me. Can you hear me?
Yeah,
yes. It's good. Fine.
Yes.
Okay. I mean, some point sound disappeared. Okay, so topic of my talk will be about, it's quite a classical. It's about scalar quantum field theories defined on ultrametric spaces and the effective potentials, which is one of the most classical topics in quantum field theory. How can we define them, and what can we see from them for ultrametric theories? Okay, so also, okay, so let's start here, and I would like to present my collaborators. So Andrei Bagrov, who got professor position in Nijmegen this year, and Askar Ilyasov, who will get a postdoc position at the same university in Netherlands also this year. So my talk will be devoted to investigation of the effective potentials in the quantum field theories with quartic interaction on the unramified extension of p-Adic field. Typically, before quantum fields has been considered on just a p-Adic field or a product of p-Adic field. So in some, so we'll follow the works by probably it will be a little bit different what was considered before. Effective potential. What is effective potential? It's the best way to visualize how quantum effects deforms the classical action and to see how it really looks like at quantum level. Field theories on ultrametric spaces are important and unusual, so it's very natural to take a look how they look like, and how quantum ultrametricity differed from ordinary, and how quantum real field theories are related to quantum ultrametric. So let's remind how the effective potential is constructed, can be constructed for a scalar field. Can you hear me? Is it okay? Is it everything goes right?
Yeah, good.
Okay. So typically, if we start with some scalar field and just with two derivatives, for example, we can turn on classical some sources and define the generation functional of all connected diagrams, which can be defined in this way. So if we here, I mean, here also we can consider it as a partition function, log of partition function. That I'm following the original works by Coleman and Weinberg, where they consider Lorentzian field theories first. Of course, our focus will be on Euclidean field theories. So the Euclidean formulation is just a parallel, can be done in parallel. Okay, so the generating functional is a very textbook things, but anyway, I will remind them because to establish a notation and proceed with calculations further. Okay, the generating function for the connected green functions is just the expansion of Dubély. If we, by definition, we can define some classical field, which is just a derivative by source, and make a Legendre transformation of this functional, which can be checked to satisfy this property. And this is called effective one particle irreducible action or effective action, or many different notations. So it acts absolutely like a W, but now it generates not connected diagrams, but all one particle irreducible green functions, which can be defined as the sum of all connected Feynman diagrams, which cannot be disconnected by cutting a single internal line and without propagators on external lines. So this definition is quite formal, and in fact one can show that effective action, for example, just to consider one scalar field, it can be represented by some function of some kinetic term probably renormalized by Z, and with some function V which is called the effective potential. It's just the first scalar term, and it is equal to the sum of all Feynman diagrams, so one external scalar lines with vanishing external momentum. Okay, just after this quite a formal introduction, let's focus on the canonical example. It's just a quartic interaction. We will mostly consider massless case, but massive case is also straightforwardly calculable, and the formula are quite simple. The role of potential in terms of the classic field phi c, and in further to phi b, phi ground, or phi classical, it's the same. It's just the same interaction. The full determination of effective actions requires to some infinite number of diagrams, and the simplest way to do something explicitly is to organize them in loop expansion. First, so this means that first we sum diagrams which contains one loop, then sum all diagrams which contain two loops, etc. So at one loop level, we have to sum all diagrams which has the form of the ring with two external lines, because we consider a quartic interaction with two external lines connected. So it will be zero level. First, it's just a ring circle with two external lines, then add two more external lines, and add two more external lines. So in each term, in this series has the form that vertex, canonical massless propagator, and some symmetry factor which is related to the rotation of to the rotational symmetry of each such a diagram. Summing all such rings, we can obtain that as effective action is explicitly summable. The expression for effective action, or effective potential, which is in fact the same, is explicitly can be summed in some logarithmic integral, and in n-dimensional space time it can be defined like this, where alpha is just a lambda phi beta squared. So we can see that for just the quantum mechanics, n equals 1, 0 plus 1 dimensional, it's finite, so nothing special occurs. For 2 dimensions, for 1 plus 1 dimensional space, this integral, and higher n, it diverges, and for 2-dimensional spaces, it leads to some supernormalizable field theory. For 4-dimensional space is renormalizable, and higher dimensionals are not so good. Okay, so our task is to investigate this integral now. Yes, for n equals 1, the integral converges, as I said, and just a function, it generates some linear terms that can be by redefinition by fields that can be eliminated, and we do not need any renormalization. And for 4-dimensional space, expanding for large cutoff, here is a cutoff that we introduce. Expanding for large cutoff, we obtain what is called in a famous work by Coleman and Weinberg about summation for radioactive corrections, imposing by renormalization conditions that effective potential should the massless field should be massless after normalization, and introducing some arbitrary scale phi 0, and phi b is what is a ground field or classical field, and after normalization we get that the effective potential has some correction like this. So this is a kind of quartic term plus log running constant. What is special with this? As we know, what is special with this potential? It shifts the vacuum. So originally we have a theory with a stable vacuum, and if we add this effective potential to a classical action, the action will look like this, and we seek how to additional minima generate. So this indicates phase transition or some symmetry breaking, and this is why really how to see how field theory behaves at a quantum level. One of the ways to investigate the effective potential. We can visualize, just make the visualization of quantum effects, because renormalization, just for example, if you consider some diagrams and renormalization, it's very interesting and inspiring, but doesn't have some kind of, I mean, with straightforward and very simple visualization. So this is why it's important. Sometimes, for example, like in famous work by Ageev, Dolan, the finite temperature, for example, can destroy this minima, and symmetry breaking can disappear. And there are numerous effects which are related to this calculation. In fact, as we know, string theory. In string theory, the derivation of Einstein equations are just calculation of effective potential in some sense. It just proceeds in this way up to some one non-trivial step. Okay, so after this, let's turn to the, probably my talk will be a little bit shorter than 1 hour. So, okay, so now let's turn to quantum fields on unramified extension, and there are numerous names who contributed to researches about quantum fields on p-Adics. So it's very hard to mention everyone. So this is just a short list, I suppose. So we mostly follow recently p-Adic and p-Adic physics has gained a new branch of investigations. It's motivated by ADS-CFT correspondence, and we closely follow. This can be seen as some kind of continuation of investigation of started in this work about ON symmetric field theories on unramified extension. So typically fields on p-Adic space has been considered, and to construct, so this is Lagrangian, and this is just an interaction term, quartic interaction term, and this here we turn it to momentum space, which can be done by in terms of Vladimir derivative, and is very standard. And S, which we consider S to be equals to mimic the standard kinetic term. Okay, so why should we consider this object instead of this object? So as was motivation from holography, that, for example, fields on just QP can be considered as some kind of object living on a Kelly tree with some prescribed branching. So and if you have objects living, if we want to consider n-dimensional fields, taking the product QP is just like taken to product of two these Kelly trees, but probably it is more natural to consider object like this, which has kind of multidimensional branching at each point, and this is how we are motivated. I'm not a mathematician, so some details of definition could be are leaking for me, but so the main point before going to some formal definitions, the main point, what's the difference between integration of cover QP and its extension of n? It's just that we have some kind of, we have a power n here in the ordinary integration formula over a function which is dependent on the norm of x. Okay, so also why we would like to consider unramified extension is that norms on external product of n copies of p-Adic fields can be non-uniquely defined, and in fact Pn is not a field by itself. So we would like to have just one object which behaves like a p-Adic field, like a canonical p-Adic space, not the product of n p-Adic space. And I suppose it would be interesting to compare these two approaches. So yeah, and explicitly unramified extension can be obtained from QP just by joining some root of unities. It's one of the ways how it can be constructed. Its definition is quite formal, so I would like not to stop on it. And of course, one can define some norm, x on unramified extension using just an ordinary p-Adic norm, and it's given by just a power 1 of power n, p as a canonical corresponds to canonical p-Adic norm, and n is a determinant linear map induced by related to multiplication and n products of p-Adic spaces. So the wisdom is just the norm on unramified extension behaves very similarly to some special norm on the product. So, but the I cannot provide an explicit form. You have to take it in each case separately. Okay, so now as we define it, the Lagrangian, we can just make some standard the same to proceed with the same story for ultrametric spaces, and here is in front of the p-Adic integral we have some kind of volume of QPN ball, and we have the summation like this, and just proceed with the same integral, but now k is taken just not just a modulus, just it's taken by norm on unramified extension. It looks like here it looks like as you can remember, the integral in Coleman in calculation of the dimensional in real field, in real valid field theory, in real valid field theory, here it was a dependence on d-dimensional space of momentum, and here we have just one integral, but due to properties of integration on unramified extension, we have that, here's the formula again, we have that we can mimic the behavior of n-dimensional field theories taking different powers of n. So let's proceed how it happens. Yeah, so our main object to investigate is this sum, where we have to introduce the regularization as in the case of some cut-off in just in real valid field theory. Okay, so it can be thought like we cut in momentum scale at some power of a prime, which can be found by this equation. So after summation, so there are two ways. In fact, this can be considered as a final answer, but if we consider it just an ordinary p-adical field theory, this answer will be finite. And for higher dimensions, we also have to introduce some renormalization and regularization and proceed as in the standard way. And there are two ways how to deal with it. The first way is to careful but rather technical and cumbersome estimation of different part of this divergent series. And it is really technical and not instructive, but it can be done, and we can obtain that the effective potential for four-dimensional field theory mimics something very similar to real valued potential. So this is the part which was present in real valued fields, and this is a part log p, and this guy, they're coming from the structure of the space, and p being prime. Okay, so just believe in me on words that we can do this estimation, but in fact, funny is that we can proceed with some very crude formula like this. So let's estimate the sum. For example, we would like to estimate the sum like in the integral form, in the spirit of Euler, Maclaurin, and for infinitely differentiable function, it would be valid if the residual term being small, but and we can strongly doubt whether we can do this substitution, just make it just exchange an integral and summation. But curiously, is the integral approximation, so we have to deal with the following integral, and if we then proceed in the absolute standard way as we do in real valued scalar field theory, we will obtain absolutely the same answer like in series estimation. So this opens the way that conjecture that we can conjecture that the integral estimation can be is very good, and for two-dimensional one plus analog of two-dimensional fields and four-dimensional fields, it gives the same answer as a agonizing estimation of different parts of series. But it's interesting to see what happens in a finite, where we have a finite answer. What about quantum mechanical example of just a QP? Okay, here is the estimation by just integral formula, and we have that some answer, and here is we can just leave series summation at which is exact, just the answer where from we start, and we have that we see that one answer at infinite p has limiting value for log 2, and another for limiting value it's 0, so which indicates that something goes wrong. But however, for not so large p, we have a surprisingly good accuracy. For example, p7, you can see it coincides, this function coincides for two digital values. So it would be interesting to clarify in future whether this approximation works well, and what is the limitation of this approximation. Okay, so yeah, and also we can try to deal with p1 limit, and in fact, we will get for a four-dimensional field theory, and for two-dimensional field theory, in fact, we'll have that Coleman-Weinberg, that one can almost reproduce Coleman-Weinberg potential from ultrametric theory, and this identity strongly relies on the following fact that just an integration on over some function over QP n in the limit to p to 1, taking limit p to b1, it reduces to integral over whole to like it's equivalent to integral over n-dimensional space. We have to put here n dimensions and some prefactor which corresponds to some sphere. So this is like we get some n-dimensional ball and n-dimensional space and integrate over it. Okay, so in fact this is approximately what I wanted to say. So probably it would be nice to mention future directions. So as we mentioned, there are two ways to define the analog of n-dimensional spaces here. It's by product of n copies of space, which leaves, for example, propagator to be, as I remember, leaves propagator to be non-uniquely defined, versus unramified. What will be the structure of divergences and what will be the advantages or disadvantages taken product or unramified version of n-dimensional as an n-dimensional analog of field. So also it's interesting to consider mixed fields. So where one of the fields is taken to be real valid, for example, and one of directions is taken to be real valid, and another is ultrametric. So would be this would be like a detecting of some hidden directions in like compactified directions. It was this kind of field was considered recently by Gapser, and the motivation was exactly like this. So it would be interesting how the effective potential would hear this small compactified ultrametric directions. And finally, it's very interesting to consider p-Adic Liouville theory with just a two-dimensional. So it's natural to consider unramified extension of second power. So natural to consider p-Adic Liouville field theory with just a scalar field theory with exponentially growing potential. It's well known that the effective potential remains the same for this field theory. This is one of the most prominent examples of conformal field theory, and it's known by its relation to string theory. So the consideration of, I suppose, is the most interesting problem to consider: how Liouville theory should it remain conformally invariant, or will we get the same exponential potential like in the real valid field theory, and will we obtain non-renormalization of wave function, and what would be the relation to string theory, because the ordinary Liouville field theory is known to be strongly related to different versions, and there are many kind of correspondences like C equals 1 theories and etc. So I suppose this most intriguing. In fact, it probably quite simple to do, because the very special structure of the Liouville field theory. Also, Liouville field theory has been appeared in description of two-dimensional black holes recently, and JT gravity, or in boundary Liouville field theory. So it would be also very interesting. So I suppose this is a point where I should stop my talk, and thank you all for your attention. Thank you very much.
Okay, thanks very much. So, questions?
Yes, I have a couple of questions and observations. First of all, it seems to me that the idea of considering unramified extension, I mean, the whole purpose of considering ramified extension is to avoid technicalities using pseudo-differential operators in QPN. But this can be done.
Can you repeat, please? There is some kind of background noise.
Okay.
Can you repeat, please?
Let me see. Again, first of all, with respect to your question, product versus unramified, most general approach is to consider QPN, which is the product of n copies of QP. The idea, in my view, the idea of considering unramified extensions is just to avoid technicalities using pseudo-differential operators. Because in the case of unramified extension, basically you use the standard results on the Vladimir operator. But this can be done. I'm going to talk about this later. I consider that case in a preprint that you can see.
So the point is that unramified extension is just simpler.
Yes, of course.
Yes,
that's the point. Okay, but the general case can be studied. Now let me ask you something about the spontaneous symmetry breaking. Did you get something in the p-Adic framework?
Yes, we'll get because just I mean the answer for QPN just is changed only by this parameter, so you can of course get the spontaneous symmetry breaking here. I mean, it would be better for me to put two answers to compare it head by head. Okay, this is just the term. I mean, only prefactor differs. Prefactor, and of course we can get spontaneous symmetry breaking here.
Okay, but okay, but I suppose that at some point you have to assume that the coefficients in your actions depends on the temperature. Okay, I'm going to talk about.
But you can no temperature is more complicated to consider. I mean, in fact you can. I mean, in fact you can consider to obtain the feature of this model. I mean, it's enough to consider zero temperature quartic potential to get spontaneous symmetry breaking and shift of the vacuum. That was the point, as I understood. That was the point of Coleman and Eric Weinberg work. Of course, temperature makes things more interesting and more complicated.
Okay. Okay, thank you. I'm going to talk about this topic later too. Okay, thank you very much.
Thank you, and sorry for such a short talk.
No problem.
Comment.
Yes.
The long list of people who worked in p-Adic quantum field theory, one should add the name of Irina Arefyeva. She made very important contribution already at the very early stage of development, and also much more recently.
Yes, I'm very sorry about Irina Arslavna about that. I was writing this list 10 minutes ago, and I was in a real hurry, so I am very, very sorry.
Okay, so some more questions? Okay, if there are no questions, let us thank the speaker again.